Welcome to my talk on 3p3, a strong, flexible privacy protocol for broadcasts. Originally, we worked in the blockchain space for privacy-preserving file storage. A blockchain is a distributed and replicated ledger of information. The information is stored in blocks. A block consists of a chain-like mechanism that refers to previous blocks, as well as a set of transactions that is the actual information that's replicated throughout the blockchain. Such a transaction contains some form of data or tokens that are transferred from a previous owner to a new owner. We can just simply think of it as some form of contract. One application are, for example, smart contracts, which makes it quite more literally to have it as a contract. Such a transaction, once you create it, is distributed in the network of blockchains. The transactions itself can have various modern cryptographic solutions for privacy, but these solutions fall flat during the distribution phase in the network. No matter how private the cryptographic solution is, once the first network neighbor sees the transactions and can associate it with your IP address, you lose most of the privacy, as the effects of the contract can later be observed in the blockchain anyway. To add privacy to this mechanism, there are various proposals made and papers published on the topic. For once, the most direct solution to adding privacy is adding onion routing in between the nodes. Every node will just use a tunnel between the participating peer-to-peer nodes and create a more private environment. This is actually done or possible in most networks anyway, so it's not rare to see in, for example, Bitcoin. But as we use most tunneling systems directly as a replacement for normal TCP connections, we often can force them to break this tunnel and connect via usual TCP, which was done by example by Biryukov et al. The other problem with this approach is that it does not natively support any broadcast mechanism and apply possible further privacy mechanisms that are possible for broadcasts. As a short restatement of our actual goals for such a broadcast, we still want the broadcast to reach everyone and be reasonably fast. Reasonably fast means that our applications are not hindered by our protocol. We also want sender anonymity, so creator of a transaction can be reasonably sure that their privacy will be guaranteed. On the application side, we will have to make a performance trade-off between privacy and performance, as we will have to sacrifice some latency for our privacy gains. But we would like this trade-off to be dynamic based on our actual needs for our application. We previously presented a simple concept for such protocol at IWCSS 2018. We can use a strong privacy-preserving protocol as a base layer, which only encapsulates a small part of the network, so we can't be distinguished even by the most strong attackers we can think of, from at least a number of different nodes. Further, we apply some statistical spreading mechanisms like dandelion or adaptive diffusion that came up in that scenario recently to gain more privacy at a lower cost or lower overhead. And finally, to reach everyone in the network, which is still an important requirement, we will use some flooding to finally fill up all the gaps. To implement the strong part of our protocol, we apply Dynamic Cryptographers network as a short revamp. Dynamic Cryptographer network of a size 4 in this case allows one user in regular intervals to share a message without being identified. We say that a message is not equal 0 if you want to send a message, and if you don't want to send a message, you set the message equal to 0. This allows us to combine them in a cryptographically secure manner without leaking the origin and reconstructing the actual message. We applied 2 rounds of Dynamic Cryptographer network to actually share the protocol based on Van Ans et al.'s protocol. We split our message into secret shares, S1 through SK, and these are constructed in such a way that our message can be reconstructed by combining all the messages with a suitable operator, in this case XOR. We create commitments on all of those messages, here CRI and SI, and publish all the commitments CI. In the first round, we forward the SIs and respective RIs that are required to compute the commitments to our neighbors with the number I. So after the first round, everyone has a set of secrets and a second set of randomness and can validate the published commitments. In a second round, we gather all the secrets of others and combine them into large S in this case, and we combine all the randomness and compute our large R. We then take both of these and publish them inside our group network of participants. So now everyone will receive these aggregated secrets and aggregated randomness. Again, we can validate the combination by the originally published commitments. We then can combine all collected secrets into as all, which is equivalent to the combination of all message parts. Further, we can do the same thing for all the randomness, and we can combine all our commitments as we are using a homomorphic commitment scheme to validate that everything in the process was correct. So if now one user has only m not equal 0 and the combination allows for a combination with 0 without a change of the message, we will be able to reconstruct the original message. We apply this protocol by using multiple slots. By using k slots, 2k slots, and each slot consists of 2 values and an array of values. First, round identifier, R, the length of message we want to transmit, and an array of encrypted randomness that we will use in a later stage to prove correctness and prevent cheating. In the second round, we construct an actual message of length of sum of all lengths L and put our actual message in the slot designated by our identifier that we shared in the first round. To share the first round, we use Van Ans et al.'s protocol, and to share the second round, we create a custom DC Dynamic Cryptographer network. As an extended example, let's assume we have 3 participants and one does not want to send anything while both other participants want to actually share a message. So they will select a random slot and place in a random identifier as long as the length of their message, in this case for hello is length 5, 5 has length 1. And the combination after the first protocol run will look like the below result, while not including big K, the shared randomness. We can see that everyone can now distinguish their entry as the 17 and 5 combination reappears as a certain slot. If we now want to construct the message for round 2, we create a new slot of length of the sum of all lengths, in this case 6. And our user that wants to share hello will place zeros in all slots that do not belong to him, and his actual message in the slot that belongs to them. We can now see that the combination of all verticals will result in just the messages one after another. So all participants can reconstruct the result once these are shared. In a second round, we now want to apply a statistical model. In this case, we use adaptive diffusion by Fanti et al., which works by selectively spreading the apparent center of the distribution graph. So we split our message dissemination into 2 parts. First, a virtual source, which pretends to be the originator of the message, and the actual message dissemination. The true originator selects one of its neighbors to be the first virtual source to pretend to be the center. The virtual source, here dedicated as yellow, while the true originator is red, will now distribute the message to its neighbors. And all participants in blue will have received the message so far. We have a second view of the network of all people that already received the message on the right, and the spanning tree it will create. The node now has 2 choices. The new virtual source, it can either deepen the tree of people that already received the message by spreading the message, or select a new virtual source node which will pretend to be the center of the graph, the spreading tree. In this case, our node decides to spread the message one deeper, while all the nodes decide on a subset of their neighbors to receive the message. They only use a subset to further decrease the risk of an attacker receiving the message and actually being able to identify the participants early. Once this process has gone on long enough, the risk is not worth it anymore, so participants will be able to freely share the message. And this selection of only a subset of participants is a parameter we introduced in our paper as mu. Lastly, we will add a flooding mechanism to finally reach the last part of the network. This will leave us with a few parameters of our protocol. On one side, for the evaluation, we have the network size and the connectivity, or how many connections are in between all participants. The DC network can be parameterized by the group size, so how many people are in a single DC network, as if all participants of the network would be in there, the network would explode in complexity. And for the diffusion, we have the depth, as in how many steps of the diffusion do we actually perform before switching to a flood and prune, and the spread of the message, how many participants are selected each step to participate. Based on this protocol, we build an evaluation simulator. Our simulator creates a network a random network at that with a certain amount of connectivity and nodes. And we display here a sample network with 30 nodes or 32 nodes to be precise. And our simulation runs through the steps of the protocol. Originally, our true originator in red and the black nodes shared a DC network of size 3, while for the second phase, the first virtual source was selected as one of the DC network participants, which then furthered the virtual source node to node 23, which would be visible to any attacker as the simulated originator. On the right, we can see the progress of dissemination through various steps of the network. We measured the latency and compared it to a simulation of various other protocols. If we use a simple flood and prune mechanism, we can expect an average latency of about 400 milliseconds in our simulation for 99th percentile of the simulation. In red, we see the 50th percentile, which is often quite a bit faster. For Dandelion, a competing protocol that's only using statistical privacy, we can see we have a 50th percentile of 800 milliseconds. The 99th percentile is not shown as it is way above the top of the screen, as Dandelion applies statistical methods that cannot be terminated directly. The worst case scenario is quite bad. On the other hand, the mechanisms used in Bitcoin natively to achieve similar things, or at least much weaker but similar things, is far beyond the chart too, as the expected latency in Bitcoin is 5 seconds for a message. The simulations of our protocols show a 99.9th percentile completion after about 1 second, which is more than acceptable for usual applications in the blockchain space, as we can compare to the Bitcoin latency here. Adaptive diffusion, implemented as we did on its own, already showed us in-between performance between our protocol and flood and prune by averaging about 500 milliseconds for reasonable network sizes of up to 10,000 nodes, which is the current size of the Bitcoin network. We already also studied the impact of the various parameters of our protocol and detected expected quadratic scaling of the group size, largely no strong impact of the depth and minimum connections within the network. Lastly, we checked the impact on the performance of this spread parameter in adaptive diffusion, which we included, and we could see that a lower spread parameter, which would increase privacy for participants, will noticeably or statistically significantly increase latency of the protocol, but not by so much that it is worth giving up the privacy it generates. As a summary, we saw that we have a problem of disseminating messages in a blockchain network. We showed we have a proposal of a 3-layer or 3-phase protocol to tackle this. We saw the results of a simulation that showed that the performance of our system is acceptable for all expected behaviors, and that it can compare to weaker protocols already established and even provide better performance due to its termination strategy in the higher percentiles of the performance distribution. If you have any questions, feel free to send me an email. Thank you very much.